Welcome to the HyperX Academy. In this video, CEO Craig Collier will be presenting on Understanding Design-to Loads with Space Potato, the new 3D load enveloping graphical interface in HyperX.
So we're looking at the upper wing skin cover load, the internal running load, the NX, for load case 103. If we were to come to the Model tab and pull up the Design to Loads form, you will note that there are 17 load cases. Some of the load cases have a limit factor that is 1, and some load cases have a 0. Likewise, for the ultimate, as typically you would see in aerospace, there's a 1.5, but other load cases have an ultimate value of 1. Let's now focus on the zone of interest here. The NX load is being plotted. We can plot the NY load and the NXY load. And of course, we would be able to do this for any of the different load cases. Let's go ahead now and click this zone. And that's pulling up the Space Potato UI. We can see that zone, and we have the default Strength Ultimate load type being displayed here. You can see the blue and green and red axis. As you note here, red is an X, negative here, tension in this direction. And what I would like to bring to your attention is the envelope here. We'll get to that in a moment, and you can see all the points for all the different load scenarios. If we turn on strength limit, you can see in purple those load scenarios, and you can see for the most part the limit load is less, but we do see one area here where the limit and the ultimate have the same value. These are not photographically scaled because, as we saw earlier, some of the limit and ultimate factors were different per load cases. I'm going to turn off the strength limit now, turn on the buckling ultimate. Even though the buckling is at ultimate and the strength is at ultimate, the buckling loads use a different load processing method than used for strength. Strength extracts from the FEA the peak loads of any element in the zone, whereas buckling is more of an average compressive load over the zone. Going to the Design to Loads tab, there's a button to select how to color. Selecting by design case, we see 17 load cases in the legend and in the Space Potato plot. Load cases are clustered together, as you can see when I toggle on and off the hover load case. It may not be clear which of these points define the envelope surface and which are interior. By coloring the interior points with green, we can tell now. Another way is by not showing them. After hiding the interior points, now the legend displays only 5 load cases that define points on the surface of the envelope. Turning the interior points back on, let's now remove from the display design cases from the legend. By turning off load cases that are on the envelope surface, we can see how the envelope becomes smaller. I'm going to turn this load case back on again, and I will turn off the GS tie down load case, and then I'll turn it back on again. And so therefore you can see the envelope did not change shape or size, meaning that that particular load case is not critical. It's not on the envelope surface. Let's turn those load cases back on. There is another way to see and to quantify the impact of a load case. We can isolate a load case from all the others by going to the load processing dialog. We can select first the GS tie down, and second, the cruise. So we're going to isolate those two and apply those. So the next step then would be to go color by the isolated design case. And you can see in the legend, the reddish color, the cruise, and the bluish color, the tie down. You can also see their relative values as compared to the design to envelope. I'll come over here and show this isolated design case load ratio vector. The yellow line extends from the controlling isolated load point, following its orientation vector to the envelope. This orientation vector in the yellow then is the same orientation vector from that point to the origin. And this point happens to be the critical element for that load case NF cruise, which is determined by which point is closest to the envelope surface following the NX, NY, and NXY orientation vector. We can go to the probe and place a label on that point and also a label on this point here. And drag that down as we saw before. The label lists the ratio of isolated load value divided by the load value where the vector touches the envelope. The higher this ratio, the closer the isolated load is to the envelope. In the case of the NF cruise, you can see a value of 0.277. So essentially, the worst element for NF cruise is only 28% of the value of the worst other controlling load case defined by the envelope. And in the case of the tie down in the blue, we can see that ratio is 0.875. You can also see by going back to the color by, we can color again by design case. And so in the case of the cruise, as you see here, the 28% is based on the NF gust, so it's closest to the NF gust load by 28%. After removing the orientation load ratio vectors, let's now go to the load processing dialog. And here you can see we've got different load processing techniques. So far we've been using the element-based processing method. Let's leave this on and include another load processing method, convex hull. Apply that, close it. Now if we go to color by unique envelope, we can see that the element base in green, this color here, producing a lot of load scenarios that you would have to analyze and optimize your zone for. With the convex hull processing method, we can see in the reddish color here fewer points, and those points do indeed define that design to load envelope. To prove that, let's first turn off the element-based processing data, and you can see that the envelope shape is identically the same as it was before, just a lot fewer points for the convex hull to get there. If we turn this back on again and then turn off the convex hull, you can see these green points here. Let's look at this part of the hull. And if I turn the convex hull back on, you can see that they are going to be identically on the same XYZ coordinates or load values, and they superimpose on top of the element based. So you're getting the same controlling load cases with the convex hull. Now, if we go to HyperX proper and we come here to our extraction methods here, we have the filtered. And now you can see the convex hull as a load property option in HyperX today. Going back to the load processing dialog, let's include this time the peak element filtered. This is a technique that has been in our software quite some time. Its legacy, it was in Hypersizer, has been in HyperX. We're going to include it to see how it compares with the other methods. So let's go ahead and turn off the element base because we know that is represented by the convex hull. So if we turn off the convex hull, this is the peak element filtered envelope, and you can see it's a little bit smaller than the convex hull one we see here. Now, what is the point of this? Well, the peak element filtered, again, a legacy method, is very fast. It is faster than the convex hull, being that it doesn't quite capture all of the load values. Most likely what would happen is your margins of safety could be a little bit higher with the filtered, and the potential sizing weights could be very, very slightly lower weight. Again, though, it is the faster method. If you're wanting to almost guarantee that you get the same weight, the convex hull would be the way to go. In the final design certification process, you would probably most likely want to assign a margin of safety using the element-based method. Let us now verify these values with our traditional pre-processor, post-processor, element-based load gradient color plots. By looking at this space potato envelope here, we can see this point looks to be probably the highest compression NX value. And we can see that this point is identified by all three methods. So let's go ahead and turn on our probe here, and we will put a label there and drag it over here and see that value is 1307.54. If I go to that same load case, vertical acceleration, plotting NX, I can see that negative 1307.54 value is there, and it's these elements. For the use case of using HyperX to process the design two loads and determine what they are. We also have the ability to export our data to your environment. You may want to use these loads to do analysis with your own tool sets. To do so, we have on this export to CSV file where we can include information to help you do that. So I'll export this and I'll call this file called video example here. And then I would go to that folder and open this. It's going to open it up in Excel. Let me bind it and pull it down. Video example, and do some just quick formatting here and see different ways that you may want to look at this. But here's an output of the convex hull and element-based method and the peak element filtered. Remember, we had all three of those turned on, so it's going to give you that information. Now, if you just wanted the peak element, you would just use that, or the element-based, or the convex hull. And from here, you can look and see what values you have. Potentially it can come over here and sort by smallest to largest. And there's your minus 130754 that we saw from the from the potato convex hull and also from the post processor FEM graphics.